Okay, so welcome back. It's great to see you. Today's going to be another very full day of material, although of a considerably more varied sort than what we saw yesterday. During our sessions together yesterday, we focused predominantly on a set of successive stages of building up a GIS-focused model in AnyLogic. And this opportunity allowed us to explore a number of features of the GIS environment on the one hand, but also of some additional aspects of AnyLogic, such as the use of so-called dynamic and action parameters to explore interventions. So within this context, we saw that AnyLogic provides a quite rich support for models, for particularly base models that draw on GIS databases. And we saw that within the context of AnyLogic, we can query GIS data, draw in information not only about sort of maps for a given area, but also information that allows agents to be routed from one area to the next along street routes, along bike paths, along walking routes. And we saw, moreover, that we could statically, and in fact it could be very readily done dynamically, change people's movement speeds on an individual basis. And we can allow those individuals to query information, for example, regarding the nearest feature of interest, whether it be a park, a grocery store, a convenience store, etc. While the interface has some distance to go to provide really very, very convenient access for all types of GIS information, it's an excellent start and better than what I've seen in any other package myself. And I think it provides a very natural place to build on for models that do involve a focus on things like the impact of the built environment and physical activity, or of the food environment. We saw, moreover, that within this interface you could select different providers for types of information, and many of you may wish to who may wish to make use of the GIS features may wish to point it to your own servers so that you can get GIS data that you've collected or to which you have access that might be more specific to your research problems. Maybe it's availability of sidewalks or green space or particular types of recreational facilities in a given area. Yesterday we started with an example where we explored this. We could add features in the form of agents to represent discrete features of the environment. And we could also query the system for resources within certain regions, or place things within certain regions. This provided us with a way of simulating the movement of agents and their behavior within the context of a spatial environment. Dylan is someone who's been making use of GIS for several models, and one of the things we may do later today is take a look at some of those models that are more articulated than what we were able to build up in a one-day session yesterday, and which take advantage of some of these additional features of AnyLogic, and which also read data, for example, regarding population distribution and create people in appropriate areas of the model accordingly. So within this context, AnyLogic is rapidly advancing. There's a big difference between what was available in 6 and version 7, and then successively, as subversions of 7 have come out, the GIS has been one of the points of significant focus. So I'm expecting more evolution of this interface and probably a richer interface over time. Both Dylan and other students that I've worked with have made significant use of some of the additional functionality. One of my students imported shape files and had some, and this was with an earlier version of AnyLogic and AnyLogic 6, and had used shape files of their own source for certain features of the model. In addition, yesterday we saw how we could incorporate within the context of that model features from hybrid modeling. So we had two features from agent-based modeling that are notable: a state chart, with which you folks are increasingly comfortable. One of the features of it we saw was hierarchical states. These are states that contain other states and that are useful for several reasons. One thing is they provide an economy of description associated with transitions between states. So you can have, for example, one transition out of that hierarchical state, that composite or compound state, this one illustrated with a clear color, and that would correspond to transitions out of each of the substates. Second of all, you could just ask, for example, is someone in this model in a food-seeking capacity right now? And it would give an answer yes or no that wouldn't have to deal with the vagaries of all the substates. You could just ask, are they in there? And over time, you might add more substates or change how things are configured. You wouldn't have to change the fundamental question of how you'd ask about whether they're engaged in food seeking. There's some additional advantages too. There's things called history states that I don't have time to go into. But generally speaking, composite states can be very, very nice. And one of the models that I believe I've provided to you, and certainly if I haven't already, I could do so, makes extensive use of these sort of compound states to mediate sort of the logic of the model. And we may take a look at that later in the day. Another feature of the model, though, that we saw for the first time yesterday was this issue of action charts. And while I don't want to focus all my comments on plumbing specific to AnyLogic, action charts are illustrative of a general feature that you seek to achieve with dynamic models in general, and that for agent-based models it's particularly important to capture, which is stakeholder and team accessible representations of model logic. We can capture a tremendous amount in agent-based models using code, and traditionally that's how agent-based models have been built. But code is a challenge in the human theater of modeling because people don't feel comfort looking at it and having a sense of what's going on. So it can make agent-based models. The risk there is that agent-based models traditionally have been vulnerable to a perception that they're black boxes, that they're things that might be really neat and incorporate a lot of assumptions, but we as the stakeholders or we as the other team members can't understand what the modeler is doing. And that's a real risk. And I have seen major projects led by absolutely top people in the US academic context, people who have reputations that are stellar in the epidemiology area, who have been saddled by models where they have hired programmers to work on them in programming languages such as Java, not in AnyLogic, but in other platforms. And they have found themselves at a position that's very awkward. They don't know what's in the model, they don't know what's out, they don't know what's enabled, what's not enabled, because they can't understand the model. It has been built up by a team of software engineers, a team of non-software engineers, but programmers, and it's impenetrable to a non-computer scientist. And that's a real problem for them. And in fact, it's jeopardized research productivity, it's jeopardized insights from the model, jeopardized soundness of the model results, because they think it's simulating one thing, it's simulating another. And it's a real virtue to have a platform, whether it's NetLogo or AnyLogic, where you have recourse to a representation that has many features that are understandable by stakeholders. And I think action charts, while they have their critiques and so on, they have a quite transparent way of displaying what we call decision rules associated with an agent. And I noted that these decision rules, like state charts, and indeed like stocks and flows, they simultaneously address this issue of what are the states, the actions that change them, and the rules by which those actions take place. The state charts can capture some aspects of state, but most notably they focus on the actions and the rules. And we had here a quite visual representation of the logic associated with food seeking or food consumption by an agent. And this logic was stylized, perhaps to the point of almost being impoverished, but it provides a general rubric for how we could expand it, maybe more than a day's time, to incorporate other features. So, for example, we could choose our meal based on price. We could choose our meal considering not just our general preference, but what we've recently eaten. We could do so based on who around us is eating things, etc. So the point is, by having a rule that's quite visual, we could show our model to stakeholders, show our model to other team members, and have some degree of confidence that they're going to be able to understand what's in there. That a lot of it will be transparent. Maybe not all, but a lot of it will be things that they can understand. And that's critical, because remember going back to the first day, my emphasis on models, not as crystal balls, but as learning tools. And if a model can help elicit comments from the team members, can help draw out critiques, you have used it successfully as a learning tool. You've drawn out institutional knowledge that was previously tacit or latent. And similarly, if by showing a model's results, by running it, you can get someone to comment on the results and say, I've never seen that. Or that's interesting, that's a pattern I see all the time. Or this looks like the type of pattern I see, but it's about twice as big as I normally see it in terms of these oscillations. That's also using the model as a tool to elicit comments. And it's a very important point about building a model incrementally. When you run a model and you show it to people, often it draws out knowledge that they hadn't mentioned yet. The fact that you show them some dynamics associated with the model, some behavior over time or over space, will often draw out knowledge that previously wasn't tapped. It wasn't knowledge that went into one parameter value or one particular description of state. It's knowledge concerning the emergent behavior of the system as a whole. And if you can elicit that, it will help you build a better model, because it will help you to attune you to the fact that, well, the model's capturing these things well, but needs improvement upon these areas. So showing models, showing their structure, like this, and showing their behavior can be really valuable for improving the quality of modeling. Okay? So action charts, to an average programmer, they're going to think maybe they look a little bit wordy. I could just write it as code, but that's not the point. The point is not, could you write it as code? Yes, you could. You could also, write it in binary. But that's not the point. The point is the human theater of modeling is extremely important. Being able to communicate, being able to elicit understanding is one of the most valuable things that a model can do. And action charts have a big role in that process. The other thing, though, that we incorporated yesterday was a hybrid component here. We had an extraordinarily simple system dynamics model. And I did so with some apologies, but it's a reflection of the fact that the literature has some extraordinarily well-documented, well-established models that instead of being one stock here, weight, there are a handful of stocks, 2 stocks or 5 stocks. Things like fat-free mass, lean mass, for example, versus fat mass, In addition, some components having to do with glycogen levels or levels associated with certain types of energy storage. And those models also can be described using system dynamics and can characterize the evolution of a person's weight, state, body composition over time based on very similar inputs, to which energy intake, and very similar outputs associated with energy expenditure, both basal in terms of basal metabolic rates and in terms of physical activity driven energy expenditure. So a hybrid model such as this can be very, very convenient for capturing regulatory processes associated with continuous variables such as weight. Okay? So we incorporated that in the model. And of course, these individuals were affected in their food seeking by their preferences for going to convenience stores as well as the distance to convenience stores. This probability of going to a convenience store that we put in depended on a consideration of distances as well as preferences. So this was all incorporated in our model yesterday, and we also had some sort of simple representation of the impact of park distance from someone's home as affecting their behavior. So simple model, fairly stylized, but it highlighted for us some of the features of GIS within AnyLogic and the potential for drawing in GIS context. As time allows today, I will be showing some additional models that use GIS, particularly for care seeking, for aspects of seeking care from a primary care physician or seeking care from a service facility. I've provided those to you as part of the example models, but if time allows, we'll run them together today. Okay, so those are some reflections on yesterday. At the end of the day, we did something, and that was new. We basically took a look at how a model like this could be used to capture interventions. And I noted that the most common way that we encode interventions in AnyLogic is with changed parameters. Now, we looked at two ways that we could accomplish that. Way one, we simply changed parameters in a static fashion. So across the entire population, for example, we changed the level of preference for convenience store meals. So we just said, okay, suppose that rather than having people going from 0 to 1 in terms of their preference for convenience store meals, we could, through some sort of intervention, lower it to 0 to 0.5. And that provides, there's no shortage of models out there, well published in the literature, that have used similar mechanisms. They change a parameter value and they see the results. Okay? They posit a certain amount of behavior change and they say, what's the consequence of that to system behavior, etc. But we also looked at a second type of intervention, which was targeted at people with certain characteristics. And for those people, we undertook some action on them. We changed them in some way. And here we posited that their preference for convenience store food will be halved. Now, I noted that this identification of particular individuals could be based on any number of things. It could be based on their location. It could be based on their distance of their location, of their home location to certain places. It could be based on their history. It could be based on their demographics. It could be based on their affiliation with other individuals, their social network context. It could be based on their eligibility criteria for some sort of benefits program. So this criteria that we put in here was decidedly simple. As I recall, we were trying to do it within about a 5-minute interval. But it was a general sort of rubric that we could roll out for much more sophisticated eligibility criteria. Now, we did put these interventions in place in and we used dynamic parameters and action parameters to accomplish them, these constructs in any logic. And we had a single event that fired off, in our case, at the initial time, perform intervention. It fired off just one time. And in general, we might want to fire an event off multiple times. So an intervention takes place yearly or monthly or on an ongoing basis. And there's other models that we could look at where we have some intervention science components which actually at a more detailed level simulate the intervention. And this gets me to my next point about interventions, ladies and gentlemen. Here we've posited whether dynamically, based on someone's characteristics or characteristics over time, we may update their criteria, their behavior, or whether statically we update our assumptions across the population about how people's preferences change. In either of those cases, ladies and gentlemen, it's a fairly blunt description. We're positing a certain level of behavior change and saying what are the consequences of that. And there are great advantages for doing that. You could see the system-wide consequences as they ripple through that behavior change as it ripples through to food-going behavior and to weight change. And that's powerful, right? You look at the health and potentially cost consequences of these changes. Very powerful, very common use of dynamic modeling. Increasingly, though, that's not that's not all we can do. That's very common. I'd say it's pretty much the standard. It's very common to see that for models, but we can do better than that. And both Jeff and I, as well as Ross Hammond, who many of you know, and Elizabeth Brute from University of Michigan, and others, have a very strong interest in seeing things like behavior change not be posited into a model. Not simply say, suppose we had an intervention which achieved this level of behavior change, what are the consequences? That's great. But actually they go back a step and they say, suppose we want to examine how much behavior change would result from certain types of intervention implementation strategies. And rather than positing and simply imposing an assumption about behavior change, we instead endogenize behavior change. So you say, suppose we provided an incentive, a tax incentive, or suppose we put in place a tax on sugar-sweetened beverages, or suppose we instituted a childhood program involving incorporating physical activity into the day, or suppose we were to build more parks. And rather than saying, okay, how do preferences change as an assumption, we instead try to see how preferences change as a result of that intervention and of that intervention implementation. And that, for that purpose, the tool of discrete choice theory, random utility theory, is one of the more valuable tools to ally with agent-based modeling. So you have individual agents, they have preferences, and from those preferences, behavior emerges. Behavior emerges in terms of choice of convenience food, convenience store food. And so rather than viewing the behavior as kind of a fixed thing that we posit, and rather than viewing simply preference for convenience stores as a fixed thing, we might actually have that evolving over time. And so increasingly cutting edge of modeling is waking up to the need to endogenize elements of behavior that have been simply posited in fixed form by parameters. Okay? So in any logic, it is very easy to simply change a parameter for alternative assumptions and run the model with that parameter as an intervention strategy, as an alternative scenario. But increasingly people are interested in models where those elements are endogenized, where they emerge from incentives, emerge from changes to the environment, emerge from changes to the financial, to the built, et cetera, environment. So just be aware that while yesterday we simply posited a change to these preferences, we might be interested in models where the model tells us how much change to preference comes out of certain changes to the education system, and then that ripples through in turn to changes in weight. Okay? So when it comes to interventions, there's a lot more we can do. And one of the choices for this afternoon will be to look at, to turn a lens to this issue of trying to endogenize some aspects of implementation science for a model. Okay? So, ladies and gentlemen, I'm going to, with that in mind, I'm going to, I think, stop this retrospective and dive into a couple topics for this morning. Before I do this, maybe I could ask if there are any questions. Yes, Chris.
A couple of things.
Yeah.
Where you sort of nested a state chart within a state chart.
Yeah. Yeah.
Is there a limit to how much you can do that? Can you nest another one within that, and so on and so on?
Indeed, you can. And maybe what I'll do is go show you here a model where we have exactly that done. This might be a model that you folks will want to open, and so I'm going to spend just a little bit of time opening it up here, and I'll see if I can get it so that you could open it as well. So give me a moment. Okay, so unfortunately it's not in the models that I uploaded, but I will upload it here so you can look at it later today. I'm going to need to find where it is right now. Okay, there it is. Yep. This is a model we provide as part of our boot camps back home, and it's in a set because it involves some collaborative connections. It's an ongoing model. I've placed it in a different location. So give me just 1 sec and I'll go open it up here. Example, okay, classes, consensus, example models. There it is, okay. And then it is in for sharing in class only, yes. And here, student models, here it is. Now, this was built in AnyLogic version 6, and so I think there may be some aspects that need to be updated, but I think we should be able to look at this, and if memory serves me, I think you should be able to run this. So this is a model which is examining a zoonotic disease. So it's examining chronic wasting disease, which is a prion-based disease with potential human involvement. Individuals within the context of this model are deer, and these deer have social groupings which depend on season, and they have a certain amount of shedding of prion that goes on. And this is a spatially explicit model. This is one of these models for which, we are positing a very high level of seasonal grouping there. Pardon me for a second. I may have to change some of these parameters. But the individuals within the move around as deer. Okay, there exists a pathology for why these deer are engaged in that behavior. Looks like they are dying out too soon or something. In any case. Let me show you the logic for this. So if we go to deer, we'll actually see a very articulated state chart with several levels of hierarchical use of state charts. And I will tell you with no small measure of pride that this model was built up by an Aussie. His name is Gregor McEwen, and he is right now a research scientist in Prince Edward Island. But here we have sort of deer behavior, and you can see there's certain type of characteristics of all live deer here. I'll stop this from running. And then there's some behavior associated with deer of different capacities. So there's movement associated with fawns, random movement associated with eating and drinking, seasonal gender-based grouping, with movement of different sorts during different seasons, during which behavior, particularly for males, can be profoundly different, and for females as well. And then we have here as well some successively layered nature models associated with disease progression and with ages of different sorts. And you'll notice how they've used these hierarchical state charts to capture sort of common things that apply for different levels of state chart. Predation, for example, versus death from natural causes, etc. So here we have a model which does illustrate and plays to the strengths of hierarchical state charts. So is that helpful?
Yeah. And can you do the same thing with an action chart? Could you go to an action which is
composite?
A composite.
I'm not aware that you can. I have the impression you can't, but Dylan could comment perhaps on that. Can you have composite actions in action charts?
Well, technically, yes, but not in a diagrammatic form, as far as I know. Like, if you want to, let's say you have action chart A, and then you have a sub-action chart you want to reuse in multiple places, then within one of those code blocks,
That's
you
true.
can just call off the
You could call it, yeah.
So what effectively action charts do is they generate Java code for a function. And if you look at the Java code, basically you are just writing a function, but AnyLogic puts the boilerplate in for you. So you can do all the things that functions can do, but that's about it.
So maybe I'll just to unpack that. Thanks, Dylan. It's very helpful, and it's a very good point that because they're functions, yes, you can nest them in a sense. So, for example, you could have eat meal, and maybe eat meal has a decision here up top. Am I alone or am I with a group, right? And maybe alone, this would be the description. So it would be eat meal is, am I alone or with a group? Or am I with a group? If true, it would call eat meal with group. Otherwise, it would call eat meal alone. And each of those would be an action chart of its own.
That's the sort of thing I was thinking about.
Exactly. And so you decompose the choice into different sub-action charts. What wouldn't be going on is visually, you wouldn't see one nested in the other, but what you'd have is sort of yes, no, and then it would call off, to the appropriate action charts, and then each of those would be an action chart all its own.
Because I imagine that would have two advantages. One, if, as you said yesterday, you start from a simple and progressively refine a model, you could have a chart here that was the simple model, and then refine each bit.
Exactly.
And also, if you're trying to show this to a stakeholder, you don't want an action chart that has a million branches.
Exactly. Very good point. Excellent point. Yes, both of those would be compelling reasons you might have an action chart. And even more than that, there's a certain amount of modularity supported. Maybe this is what you were getting at, Chris. Modularity with this. So, maybe eat meal with others would be its own action chart, and you could use a very simple version, but Dylan could be developing a more sophisticated version, and you just plop it into your model, and suddenly you've got it using a much more sophisticated view of social eating. And the fact we eat more when we're together with others. There was a very interesting study that just came out this past week about men eat more when they're with women. We were looking at the NCDS, the National Childhood Development Study, where we've run some statistical analysis, and we found that we're very interested in weight gain over the life course, and particularly associated with pregnancy. And we were interested in looking at how people's weights changed with pregnancies, and we noticed that there were indeed significant weight changes associated with life events associated with pregnancy for women. But then I found that men's weight was also rising when they got married as well. And I thought, what is going on here? This is very strange. And it seemed that when there were children added to the family, men's weight also went up. And I thought, that doesn't feed into too clear a picture about what's driving things. But it turns out this latest study did show that men tend to eat more when they're with a woman, which is interesting. In any case, Of course, they may eat healthier when they're married. That's another matter. But in any event, here we have the potential for putting in place hierarchical state charts and having a certain amount of modularity.
And then presumably that would help you keep the model current, because as new results come along, you can say, okay, I'll change this bit.
That's right.
Which is just add in another.
That's right. It would minimize the amount of propagation of change. So your changes could be focused on that sub area of the model rather than affecting everything across the model.
Exactly. So you've only got to know that that sub area is right, and then the whole model is still right.
That's right.
Yeah.
That's exactly right. So if you refine that model, and someone could be working to refine that part of the model while another person works on, the individual eating representation. Mm-hmm. So you can have a decomposition of roles and so on. Any logic is, in my mind, in Jeff's mind as well, I think. It's really got to catch up as far as group model building, like having the capacity for multiple people to be modifying model at the same time, running it interactively, showing the results to each other, but also working on different pieces. Right now it's encumbered by a desktop interface, and they're very open in the multi-year time frame of having increasing amounts of web components to it, but we're trying to push them more aggressively to a Google Docs type situation where you could have multiple people operating on different components at the same time and building up a model and using the model simultaneously, which would afford that sort of flexibility of substituting end pieces, etc. Okay, any other questions or comments? Yes?
Just a quick thing, in terms of that tier model, you
yes.
had obviously slider controls to change the parameter values. Is that basically just from the controls menu, the one with the slider button?
Well, no, there's two places. Okay, great question. So there is this this interface here, and this is, Jeff talks about the challenge of these boot camps being. Why am I seeing that? The challenges of these boot camps being figuring out what's the 95% I don't talk about. And one of the things that's really easy to do in any logic, this can be done in half an hour if we want to do it. You can add these sort of slider bars to your model. We actually added something like this. Do you remember something we did? We added a button, remember that? And you can add these slider buttons, and those can set parameter values for your model. What these are really doing is basically they're determining the values of parameters, which are then used to run the model. So it's nothing that much different from what we've seen. It just provides a visual way of setting those parameters for a given experiment. And this is way that certain common parameters are set here, but those parameters can also be specified directly within the experiment in the way that we've chosen it. So here you see the assumptions that are being used. For example, for the initial case, the initial number of subclinical non-shedding deer. So these are cases that are deer that are infected but not yet to the subclinical level, and they're not yet to the clinical level, and they're not yet shedding. The hunting allowance allowed for deer, etc. So these are assumptions captured in the form of parameters. Each of these is a parameter in main. That's why we can specify them in the experiment. And in that other scenario, that other experiment we were looking at, they are set by, some of them, a subset of them are set by these slider bars. Okay, so if we went and looked at that experiment, diverse water sources, there's a use here with these sliders. If I went and I looked at this slider here, you can see that it sets it works here, and it's basically default displaying the value of this number of deer. Because this was in an older version of AnyLogic, they weren't using the features that you do now. But you can, for example, say I want to link this to number of deer, and then it just links it up. So when you slide it, it automatically changes this variable, which is very convenient. And that variable can be passed as a parameter for main. Okay. Any other questions? I welcome these questions. These are great. Okay. It seems the train has arrived, so we're going to